Tom Wilson, born Thomas Putnam Wilson, in New York City in 1918. Actually, my family at the time was living in Texas, and my family decided there weren't any good obstetricians in Texas, so my mother moved to New York City to be near the good medical help. I left there at the age of about 12 months to go down to Texas and live there for a while. I grew up traveling around. My father had a ranch in Texas, which he lost in a drought down there. He ended up running a hotel in Muskogee, Oklahoma. And so we lived in San Angelo, Texas, Muskogee, Oklahoma for a while. We went out to Sausalito, California. And then my father died, and that when I was about age 10, and I moved to the east. My mother got a job in the public library in Washington, D.C. We lived there for a number of years. That's where I went to high school, Western High School, and then went off to college. Some friends' recommendations, I applied to Amherst and was accepted there, had a scholarship. Well, I was trying to think whether there any early influences along the lines of catalysis there. One of the professors was Ralph Beebe, who people who are knowledgeable in the ancient history of catalysis and chemisorption might know. He worked for Hugh Taylor at Princeton and then came to teach at Princeton, but he kept some research going and had some ideas about physisorption. Also, I met Hugh Taylor for the first time there. And I got interested in science and felt I was as good at that as at anything else, so I went on to graduate school. Had a choice between going to MIT and going to Harvard. My uncle had gone to Harvard as a chemist, and I decided that was pretty neat, so I decided I'd go there too. I ended up working for E. Bright Wilson as a infrared Raman spectroscopist, molecular vibration type.
What year was this?
1939 was when I graduated from Amherst, and I left Harvard in 43, right in the middle of the war. Came back in 44 in January, I believe it was, to, I could be off by a year. I could have gotten out in 42. Yeah, I got out in 42 and came back in the winter of 43 because the subs were off the East Coast and they were cutting into our oil supply, and everything had to be blacked out, and the rooms were kept cold, and I damn near froze studying in cold rooms. But anyway, we got through all that. I also met George Kistikowski there. He was prominent among the scientists. And after graduating, I looked around for something that would keep me from getting shot. Went to work for M.W. Kellogg, which is an engineering firm, who had just gotten through inventing cat crackers, I believe. It turned out that they had taken on the job of engineering and building the first diffusion plant for A-bomb. So when the Kellex Corporation was set up as a wholly owned subsidiary of M.W. Kellogg, set up for bookkeeping and other purposes, I went along to Kellex Corporation and worked all during the war on that, which is why I was never drafted. I got excused on a couple of appeals. It was a very interesting time. We were working 60, 70 hours a week, and there was a lot of pressure because we knew at the time I went on, they were telling you what you were working on and what the potential was. In fact, they exaggerated it. I mean, the story that I heard was that if Hitler dropped the bomb on New York City, why, it would wipe out the city and make the state uninhabitable for the next 5,000 years.
Now, where was this you were working? Where was the lab?
The lab that I was working at was initially in Jersey City, at the old M.W. Kellogg plant there. That was later shut down, and I went to work in a place called the Nash Building, along with a lot of people from Columbia who were also on the project, and worked up there while they were building the plant, once the engineering work had been done.
And what aspect did you work on?
Well, I worked with Bill Libby on barrier construction and testing, the diffusion barriers. It was a very interesting, challenging sort of job. All the chemistry was new. And it had a lot to do with surface chemistry too, because the barriers were such high surface area materials that you had to consider the interaction. In fact, you had to consider the plugging of the pores by the molecules of UF6 in figuring what the permeability of the barriers would be. The pores were that small. And you know, in addition to meeting Libby, who I worked for in New York, I met Emmett and heard some more from Hugh Stott Taylor.
How did Libby adjust to applied research?
Well, very well. He was very confident, very quick. He was known as Wild Bill, and everybody tried to keep him out of the laboratory because he would go in and charge around and make a mess out of blowing glass and break things. He was much better off in the office and theorizing than he was actually doing work. And Hugh Taylor was, I remember going to a meeting with Hugh Taylor early on and running into him there. I was making a report. I was doing some things at Kellex, and there were people doing them at Princeton under Taylor's direction, and I guess also up at the Nash Building. And one of the things you had to do was to fluorinate the barriers before you expose them. Lay down a layer of fluoride to prevent it from interacting with the uranium hexafluoride and plugging up due to the deposit. This was done by treating it with fluorine, and after the first couple of them had caught fire on first exposure to fluorine, why they figured out that they had to have they had to dilute their fluorine in nitrogen to prevent the very rapid diffusion. The fluorine-nickel reaction was very fast and exothermic, and once it got started, if there was an infinite supply of fluorine, the thing would go off like a flashbulb. And you couldn't just mix them in a cylinder. You couldn't just put two of them in the cylinder. You had to mix them, and there was some discussion about what the proper procedure for mixing them was. And the people from Princeton said, well, they put a dry ice collar over the neck of the thing, and that caused convection currents that made it mix up. And the people from the Nash building said, well, they stuck theirs in a heated cylinder, and I ended up, I had figured this out too, and I had put it in a hot bath and then put dry ice on the top too, or ice. I think it was ice, not dry ice, because the dry ice might embrittle the cylinder. Anyway, he turned to me and he said, "Don't you think that's a little bit of super erogation?" I went home and looked that word up. He had a great command of the English language.
What kind of a person would you describe Libby, and how did he interact with people at that time?
Oh, he was a very bright, enthusiastic, hard-charging guy who could go through a report, turn it over page by page, and make and understand what was in it, and make comments, make sensible comments on it. I was impressed by Bill. Actually, I started to go out to University of Chicago. Well, I didn't start to. He asked me if I was interested in going out to the University of Chicago with him. He had some ideas working with carbon that he thought were interesting and would I like to help. I said I didn't think so. I wanted to get into industry and not into an academic job. I sometimes wonder if I shouldn't have gone with him.
And what were your impressions of Beebe?
Well, one of my principal impressions was of Beebe at a fraternity party. He was quite short and very bald, and I can remember him at the bar with his bright, shining head sticking out from over the bar. That's about all you could see of him. The lights glaring off the bald pate. He was not as forceful a character. He was a very nice guy. He was not in the league with Libby or some of the other people, or Taylor or anybody like that. They were just so good.
And did he interact a lot with students, undergraduates?
Beebe?
Yes.
Well, yeah, he was teaching undergraduate courses,
Mm-hmm.
and I took his physical chemistry course. He was not. He gave a good course, but I would assume his is the only physical chemistry course I sat through, except for Bright Wilson's. When I went to Harvard, I was a assistant in the phys chem lab and working for Wilson, and I sat through his course just to see what was going on, and there was a big contrast. Bright Wilson was so organized and so thorough about putting his writing up his little notes and then talking about them, the whole thing. If you took notes as he wrote it on the board, you had a beautiful set of classroom notes after Beebe was through. There was no question, or after Wilson was through. But I think Beebe did an excellent job, and I guess I did. My senior year, I did some undergraduate research for Beebe, with Beebe, we got to talking a little bit. He was very easy to know. Enjoyed the students, I think. As I say, he didn't make as much of an impression as some of the other people I met.
How did you come to work for Bright Wilson?
Well, it wasn't the name. That's not entirely clear why I came to work for Bright Wilson. I think somebody said he was looking for somebody to work for him, and I went around and said, I'm available.
And what did you do under it?
Well, specifically, I did molecular vibration studies, which involved Raman and infrared spectra and molecular vibration calculations on two molecules. One was trideuteronitromethane and the other was cyclobutane. The trideuteronitromethane was a continuation of something another one of his graduate students had done. And there was some ambiguity in the results that he wanted an answer to, which is why he got me to deuterate the nitromethane and then run the spectrum. And the cyclobutane was done because it happened to become available. Somebody had found you could make cyclobutane by photolysis of cyclopentanone. You form the diradical, which closes up, and so I made cyclobutane that way. And I decided that photolysis was a tough way to make very much product. I ended up with about 2 cc's of cyclobutane after working at it and down there electrocuting myself.
Now, how did he run his research group at that time?
Well, at that time, he was spending most of his time at Woods Hole.
That's what I was going to ask about.
And, so he didn't spend a lot of time there. I'd come around and talk to him every week or two, and had a general idea of what I wanted to do. And that was about it. Which is why his name didn't appear on the paper. Which I think he was sort of grateful for, because there was one thing I missed was the fact that cyclobutane was not planar, or at least it's floppy. And I think it was Pitzer who picked up the fact that it was.
And
felt a little sorry about that.
And Kistakowski was there at the time?
Kistakowski was there, yeah. But I didn't work for him, and he was away. I guess he was working on the atom bomb by that time. And so I didn't see very much of him at all.
What was your impressions of going to school during that wartime period?
Well, the professors weren't around very much. And there were some mysterious things like great long chromatographic columns set up in the stairwells that had this greenish fluorescent solution in them. Question on the exam about how do you separate uranium isotopes. But I don't know. There was considerable pressure to get your graduate work over with and get out and do something.
Mm-hmm.
But I guess, and there were no cars around. So, another thing. It was, it's hard to compare with anything else. Not having been there during your...
Who were some of the other faculty members at that time?
Bartlett. Paul Bartlett was one. Louis Fieser. I didn't take a course from Bartlett. I took beginning organic chemistry from Fieser. Who was the... Forbes, Professor Forbes. Was he the fellow who was doing the atomic weights? There was a guy there who was doing atomic weights. They told a story about, this was done in the days before mass spectrometers, and there was all sorts of very careful, painstaking gravimetric and titrometric analyses. Mm-hmm. Somebody came in and found that whoever the guy was, and I don't, it may not have been Forbes. I think it was somebody else. Had spilled had dropped out of his pipette a little puddle of solution, of this carefully calibrated solution. And he was in the process of retitrating, of refilling this area to exactly the same level as the original spill so he could find out how much he'd lost. He says, if I spill it once more, to hell with the damned atomic weight. Who else was there? There was a very small class of graduate students. I know that. Herman Nerto was there, graduated with me. His wife Dorrit's the editor of Chemtech now, or assistant editor. And who is the fellow who ended up going into teaching? Who he worked for Kistiakowsky, and Kistiakowsky had a setup which enabled him to measure temperature changes. A thermopile system. It was very sensitive to temperature, and this fellow learned how to make the thermopile and eventually went into business for himself, making them and selling them to various colleges around the country. He ended up helping assemble the atom bomb down at Los Alamos, and went from there to a teaching job at Brown, as I recall. Then there were some people who weren't quite that good. There was a fellow by the name of Art Silikowitz, a Brooklyn boy, who changed his name to Arthur Lionel. He was a student of Kistiakowsky's. Kistiakowsky was an absolute genius with his hands. He could do anything in the laboratory and had the most complicated sorts of equipment. One of the things he had this guy doing was measuring specific heats of gases. There was a whole vacuum rack, whole rack full of glassware that was involved, and the heart of it was a quartz. I guess it was a quartz spiral manometer, which Kistiakowsky knew how to make, and this guy broke one, and he couldn't do the glass blowing, let alone the quartz blowing. So he had to go tell Kistiakowsky, and Kistiakowsky said, all right, I'll come down and fix it for you. Here, you hold it here and here, and I'll blow the quartz. And he proceeded to do the quartz blowing. Well, it got hotter than hell out here. It burned this poor guy almost to the bone, and he just didn't dare let go. He eventually ended up as a whiskey taster for Seagram's.
Well, back to the Manhattan Project, then. What did you do there? Primarily, you were looking at the diffusion.
Well, we were involved with the diffusion process, with the actual membrane that did the diffusion, and I was doing applied chemistry, working on the design of the barriers, and also just on other plant operations, like what do you do if you have a sudden spill of the contents of the plant. You don't just blow it out into the air because it's toxic and unpleasant, and so you have to find a way to absorb it, and if you absorb it on carbon, it gets too hot and then it catches fire, and so what the hell do you do with it? And so we worked out a system for soaking it up without excessive heat.
On what?
Generation, on carbon. Carbon with a lot of alpha alumina in it to provide the heat capacity, so that you change the heat capacity absorption relationship. Then you had to worry because if you mixed up activated carbon and alumina, the thing was, and poured them into a vessel, the carbon would hit in the middle and bounce to the outside, and the alumina would all sit in the middle, so it would unmix, and that didn't work. So you had to figure out a way to get it in without having it unmix. Yeah, it's a cut and try type of process. I guess in the course of this, we had to handle a fair amount of uranium hexafluoride. The worst thing that happened in the course of it, I guess, was when I overfilled a cylinder of uranium hexafluoride that I was going to use to feed a experimental unit that I had. And I decided, well, maybe it'll work. You heated it up in boiling water or heated up in hot water. Had about 5 kilos of uranium hexafluoride in it. It heated up and got within 5 degrees of where I wanted it. I was all set to, standing in there, all set to turn the valve on, and the damn thing blew up. And, oh man, what a mess. I didn't stay around very long. I got sprayed with this stuff and headed for the shower. But this white cloud took over, billowed out into the offices, all through the laboratory. They evacuated the building. They had to pull the telephone operator away from the switchboard because she was going to go down with the ship. The poor safety manager had never had any real safety problems before, and he wasn't quite ready for this. So he came out of his office with his gas mask, stuck that out outside the laboratory, went back for something else, and just as he came back, they piled me into a station wagon to get me to the doctor and ran over the gas mask. Meantime, the Manhattan Project offices in New York had been trying to get the laboratory, and it was completely unable to reach us. Incommunicado. They thought all sorts of things had happened.
Could they have done the Manhattan Project under the environmental conditions today?
The environmental conditions. That was the least of our worries. What we were trying to do was save some environment. Oh, I don't know. I suppose they could have. Things obviously are different. I remember my wife talking about going over to being driven in a station wagon over to New York City with a cylinder of fluorine in the truck and smelling the fluorine all the way over because the cylinder was leaking. So we were a little casual about the safety things. Yeah, it was a different time and different techniques. But after that period, things sort of went downhill, actually. At that time, you bought equipment just in case you might need it sometime. Stowed it in the circular driveway going out this building. It used to be a parking garage that we were occupying. As an example of the priorities, I guess I should tell the story about that. It has appeared other places, I guess. They were building a power plant to supply the power to operate the diffusion plant down at Oak Ridge. And it was going to be one of the biggest power plants anywhere in the world. They got around to putting it together, and the military, meantime, had requisitioned all the copper, had a lock on the copper production of the country. for brass for the shell casings and things like that. And so the Manhattan Project figured out a way around it. They simply went around to the Treasury and said, we'd like the silver that's in Fort Knox. And they built the bus bars in this power plant out of silver, which after the war were returned to Fort Knox, but in the meantime they'd served a very useful purpose. But you don't often have that sort of priority. Of course, I came to carbide when carbide was making more money than I knew what to do with. And that got less and less to be the case. So, as I say, things sort of went downhill in a way.
Well, how did you come to go to carbide then?
Well, I had actually worked for carbide the last year that I was on the Manhattan Project. And when the Manhattan Project finally folded up, the question was whether I would go down to Oak Ridge or accept an invitation to come down to South Charleston, and I chose the latter because carbide was an absolutely outstanding chemical company and doing great things. It sort of was in line with what I had hoped to get into, so I was very happy about it.
What was it that you got into?
Funny you should ask that. Fisher Tropsch. Yeah, we came down. We were the old so-called HN department, and our job, our assignment was to provide raw materials for Union Carbide. The accepted wisdom at that point was that the world was going to run out of petroleum, probably sometime around 1950 or 55, and we would have to go to some other source of raw material. And the South Charleston plant was had bought actually large reserves of coal in anticipation of this. And what we were supposed to do was to figure out how to set up a chemical industry based on coal instead of natural gas, which is what carbide's chemistry of the time was based on. So they had two routes which they followed, both of them taken from German work which was directed along these lines during and before World War II. One was the Fischer-Tropsch reaction and one was the coal liquefaction reaction. The coal liquefaction work had been going on. There had been pilot plants there before the people from the Manhattan Project got down. We started the Fischer-Tropsch work when we got down there, and that's what I was involved in. We did get involved later on in the coal liquefaction aspect of it too. That was the start of my disillusionment with accountants. The rules always seem to change on what would make money and what wouldn't make money. And how did you price propylene vis-a-vis ethylene, and what the other hydrocarbons were worth, and if you valued them at the same price as ethylene, you could make a bundle of money, but if you had to burn them, then you couldn't make any. So there was the economics which were presented made Fischer-Tropsch originally look good, and later on it turned out, as somebody looked at them in another way, there was no possibility of making any money making hydrocarbons out of Fischer-Tropsch. However, the fact remained you could make some money making oxygenated products, because you would pay as much, you get as much for the oxygen as for the carbon in them.
Mm-hmm.
Well, the Fischer-Tropsch thing we carried to this point, to the point where we could make olefins, albeit not a very practical process. And they finally pulled the plug on that that approach, and we all went to work on the coal liquefaction. And by that time, they had a pilot plant running down at Institute. Was it a ton a day or something more than that, maybe? Pretty good-sized operation. To my view, good-sized equipment running.
What was the process?
Just about like everybody else's process. You made a coal paste by mixing pasting oil from the process with powdered coal. Put some catalyst in and heated it up. I guess the thing that the engineers at Carbide did was to say, why don't we run it in a tubular reactor? They had some experience with that in cracking furnaces, for example, where they had these tubes going back and forth in the cracking furnaces, and they made tubular reactors to make ethylene oxide, and there were a lot of tradition, and they thought this would be a good way to keep it flowing along at a good rate. Oh, polyethylene was another one, which could have plugged up very easily, but didn't if you ran it in a high enough pressure in a tubular reactor. So they thought that was a good idea. And they built a tubular reactor. And the early days, they used to have presentations on what they were building, and George Felbeck got to be so famous for drawing this tubular reactor on the wall. They said, "Oh, there he goes pissing in the snow." Again. Well, the problem, as in most of these things, was getting enough oil to recycle so that the process was self-sustaining. And I don't know that that was ever done. It was pretty close to it. But they were still looking at ways of recovering more recyclable oil. The work stopped on the process when they discovered the oil fields in Saudi Arabia. It was obvious the world was not going to run out of oil, and coal was a hard way to get there, unless somebody came up with an absolutely unexpectedly cheap way of making hydrogen. The hydrogen cost was the thing that really killed it. So we went on to try to make an honest living making chemicals at Carbide. Yeah, let's see, what did I work on? Variety of things. I guess actually I started working on polyethylene after that. We had some fun doing that. I wrote a paper on so obviously we didn't do any, Carbide didn't make any money on it. The project we worked on is a soluble catalyst for making polyethylene. Actually, it was pretty slick, but it did have problems. And I got more over into, let's see, we did that. Then we started work on the fluid bed process for making polyethylene. We originated the work on that. And I followed along with that. I got more into management. I was given supervision of the development work on that process. Saw it through the commercial scale operation down at Seadrift. And that was really very satisfying. That's probably the most satisfying thing I got into, because it actually came to some fruition. And other than that, nothing to brag about.
Well, how did you get into catalysis?
Well, it started out with Fisher Tropsch work. That was the, I had a pretty good background. With being around Emmett and Libby and BB and others, I was prepared to, at least I was familiar with the BET theory and some aspects of the chemisorption, some of Taylor's ideas on chemisorption. I was prepared to treat the surface as something that had its own problems and was worth investigating. And it's sort of interesting because it's there was still an element of witchcraft about it that appealed to me.
How did you switch to homogeneous, or?
Well, the homogeneous thing came along just because it turned out there was because the guy by the name of Welly Walker came up with a soluble homogeneous catalyst, with a soluble chromium catalyst, which was about as good as you could possibly get. I mean, it was orders of magnitude faster per chromium atom as catalyst than you would calculate would be possible for the collision number and the activation energy. The chromium was being used more efficiently than that. The only way you could explain it was that the ethylene complexed with the chromium before it reacted, and that the reaction occurred with the complexed ethylene so that you didn't depend on a collision number. There was always ethylene there. It was not faster than the collision number.
Mm-hmm.
And that was sort of intriguing because you could figure out something about the mechanism. The homogeneous catalysts have a lot easier time of it than the poor heterogeneous catalyst types. They've got a single center, and you can only coordinate about 6 things, and maybe 8 with uranium. So you could learn a lot. You could learn a lot of detail about what went on. Like in this catalyst, it turned out that if you coordinated one ethylene, you could get ethylene polymerization. If you coordinated 2 ethylenes, and then another ethylene came along and reacted, you ended up making hexene 1 all at one time, and all in one blow. The thing depended on the square of the ethylene concentration, which means it depended on the square of the doubly coordinated ethylene chromium complex, 2 ethylenes per chromium. And it turned out that was the ethylene, the hexene that was made had been cutting down the density of the polyethylene that was produced because it introduced side chains. It would further react in the polymerization. It co-polymerized to make low-density polymers. If you could prevent this from taking place, you could prevent the trimerization of ethylene from taking place by adding butadiene or chloroprene at a level which was within a factor of 5 of the level of chromium, which was of the order of 2 parts per million in the solution. And it coordinated these 2 sites without interfering with the polymerization. So you were not, you could no longer get the trimerization, but you could run the polymerization.
Now this was just by trial and error, or did theory lead the way?
Theory led the way there. I mean, we knew that the hexene production rate depended on the square of the ethylene concentration, and therefore if you put in something that tied up two sites more strongly than ethylene, you ought to have some effect. Well, it was worth a try anyway. It didn't cost very much to put in a little butadiene. It worked like a charm. So,
How long then did it take to be able to write this up?
oh, good Lord. Well, it didn't get written up until a couple of years later anyway, when I happened to have some time to put it together. I wrote it up, actually I wrote it up to present for, what was it? It was either the Amsterdam meeting or the London meeting, I forget which it was. I went back and reviewed the manuals and that sort of thing that we had put out. It had all been written up in fairly good detail. Beforehand, it hadn't been written up in form suitable for publication. And once you looked at it as a publication, more things began to fall into place. Like it seemed the center, I hadn't really thought about it, but it seemed the center had to be a 3-coordinate chromium-3, which is not easy to get. And it's one reason that it coordinated so nicely with ethylene, for example. Chromium-3, you know, wants to be octahedral, and it will, that provides considerable energy for this complexation. It means you get a very stable olefin complex. Of course, if there's anything else in there that complexes better than the olefins do, then you're in trouble. But that was one of the things that came out of the review, going back and looking at it the second time.
How did carbide keep the applied research going and still maintain this basic research atmosphere?
Well, the putting together the paper and publishing it, I spent some of Carbide's time and some of my time. The manual that was put together in part because the process was tried commercially in a plant in Canada, and it could not compete with the fluid bed process because it involved a solvent. But by that time we had gone through all the chemistry and we knew pretty well what it was. It was just a matter of extracting what we could out of what we already knew. And as I say, this is one case where some fairly fundamental ideas enabled us to solve practical problems. We wanted to make high density ethylene. You had to know how to prevent hexene 1 formation, and that came out of the fundamental chemistry of the reaction of the catalyst site. So I guess I have always felt that some basic scientific knowledge of process is useful in almost any research. I'm sure there are limits. I don't want to say that that's true in every case. In any case where you have some real research, where you have to break new ground, get new information, learn new things, I think that basic information is helpful. If it's something that you can get out of the textbooks and stick in a pot and have it run, then all right. That's not what I think of as research. It's development.
Who would you mention as some of the most creative people you've encountered through your career?
Oh, that's an interesting question. Well, you have to go back to the professors, I think. I think, Bill Libby's obviously creative. The Wright Wilson was creative mathematically. I think Gabor Samardzai is a creative, fertile mind. Werner Shoemaker was very good, and he could work. He could come around and talk to you. He was a consultant at Carbide for a while. And he worked at Carbide actually. He worked at the lab up at Tarrytown. He had worked with Pauling on X-rays. I don't know whether you remember the name or not, but he eventually left Carbide and went out to, I think, to Washington, University of Washington, and took on a professor job out there. We still had him come back as a consultant, and he had a very good fundamental background in science, and he was very useful to talk to. He'd have ideas. As far as an industrial, I'd have to think about that. Seems to me Mr. Roth has been pretty creative, from what I know that he's done, the rhodium work that he did. There are a lot of able people, but you're talking about a little more than that.
Yeah.
I was interested. Maddox is a creative guy at Stanford. I've had tried to figure out. We at Carbide tried to get him to come to Carbide to lecture us, and we were interested in having him as a consultant. And I never could figure out why he was very reluctant to talk to me or to anybody else associated with Carbide. And I finally realized he was a consultant last night.
Oh.
He's a consultant for Monsanto. And I didn't realize it.
How does one keep a youthful outlook in doing industrial research?
I don't know. It may be hard today. The atmosphere has changed.
Yeah, how would you describe the changes?
Well, mainly it's the problem has gotten to be so much short-term oriented. You almost have to have a clear short-term goal in order to justify any research. Partly, it's understandable based on the inflation rates. I've put together a talk when I was over in Changchun that month. They wanted me to talk about how Carbide chose projects to work on, and I put together something I'd been thinking about, and it wasn't really what Carbide uses that I know of, but it fit exactly with what they have done, whether they know it or not. As the inflation rate goes up, the future value of any development that you have goes down. The net present value of the money goes down as the inflation rate goes up. So you end up not being able to justify anything if it doesn't mature within 10 years. And you'd rather have something that came out next week or next month. So you concentrate on short-term projects, and you really can't do exploratory work where you can't see the answer. uh, in that sort of a climate. I think that's something that the Japanese are able to do. It's just as they are willing to. I don't know whether this is economically justified. It may catch up with them. But the fact is, they're willing to take a low interest rate on money. 2 or 3% returns is adequate for them, and they'll buy property that will give them only that. And if they figure that's all that money is worth, then long-term research is worth more, a lot more. But if you go to a time when there's 10% inflation or 15% inflation, forget it. Don't do long-term research.
How did the Chinese react to this?
The same way they reacted to it. The same way they reacted to everything. I didn't say anything. That it really was sort of discouraging to talk to them because you got so little feedback. The only comment, as I recall, that I got on that was from some woman who wanted to know how industry justified, what the heck was it? Justified not giving you a share of whatever your discoveries earned. It was a political question. I tried to explain that you wouldn't have had the opportunity to work on it if you hadn't understood that this was the way things were going to be. If you didn't like it, you could go somewhere else. And,
what was your impression of China?
that they have an awfully long way to go. That they'd like to make a great leap forward. They buy fancy equipment. They get X-ray machines that record and they can collect data over 24 hours. They buy fancy NMR machines. All these things that cost $500,000 to $1.5 million a throw, and then they put them down in a place where the power runs maybe 5.5 days a week. They don't know what the voltage is when it's running. They have water leaks all over the corridors. They don't have any sanitation to speak of. I find it hard to see how they manage how they're going to be a big factor. They may, but it strikes me it's got to be another 20 years before they get to the place where they're really contributing. When I was over there first in '82, they were still not aware of what was going on in Western journals at all. I think they probably have solved that. I think they do read. They have Xerox copies of all the journals in their libraries. So they are not as facile with English as they really need to be. I haven't any idea how much of what I said in my 2-hour lectures were comprehended by them. Well, all right, I'll take that back. Were comprehended directly. There was an English there was a translator. I had a translator. But I don't know that there were many of them there who could have understood me directly. So I think they have a long way to go. They have to come up to date on the literature. They have to develop their own programs and then bring those to fruition. And it strikes me that that's going to be, before something really good comes out of it, it's going to be years. if it happens before the year 2000, I'll be amazed. If something really good comes out. They do have a lot of people working, and a lot of interest, and a lot of enthusiasm. And they work very hard.
Mm-hmm.
And I guess the people coming over here are going to be pretty much up to date when they get back. If they have, but then they'll have to fight the equipment problem, the health problem. So it's going to be a slow process.
Well, what have we overlooked?
What have we overlooked? I don't understand what.
Well, have we overlooked any areas that we should include?
I think. No, not really. It's been fun working over here, I might say. I've enjoyed it. It's a nice way to sort of back out slowly. So I thank you very much for the opportunity.
Well, we got more than what we gave.